for this international webinar. This webinar has been organized in the view to foster the progress in research field and brings together the greatest minds in the field of material chemistry to promote quality research and a real world impact of research in academics. I welcome you once again for this event. The title for the webinar is Innovation and Application in Material Chemistry. Now I request Principal Madam Professor Vrinda Borkar to share her views and address the session.
Good morning, all, and welcome for the international webinar on the applications in materials chemistry. This has been organized by our college in association with Meiji University, Japan, with whom we have the MOU signed, as well as BITS Tulani, KK Birla, Goa campus. With them, recently we have signed an MOU for research. So welcome again to an international webinar on innovation and applications in materials chemistry. At this stage, let me welcome Professor Takahiro Maruyama as well as Professor K.S. Sarane, both of them to this webinar. The topic of the webinar has been chosen as innovations and applications in materials. This is because I feel that this era is of materials. Different methods of material synthesis has been designed and tailored to meet the applications. And that is why applications as well as the synthesis part is very important when we are talking about the materials. The materials can find applications in different areas. The main focus is always environmental issues. As regards the environmental issue, we all know, we are aware that our generation has created so much problem of pollution in this world. Last 50 years itself, there is a problem of pollution, and it is due to the man-made materials, dyes, plastic, many more things. So we have to ourselves find out the solutions for it. And if we are not finding the solutions ourselves, it means that we are leaving this next generation without water, without good environment, and maybe many more ailments which will occur because of pollution. So it is high time that it is not enough to be aware, but we have to seek the problems, solve the have the solutions for all the problems. With this aim, we have now organizing this international webinar. Now, when it is a webinar, we have observed that those who are interested definitely join this webinar and get to know what are the happenings all over the world in this area. We have added also in this webinar virtual tours to Japan as well as to BITS Pilani laboratories. That is because we have a tie-up and our students and one of the teacher had visited Meiji University in past and they were very happy with that university and its culture, research culture. So, in order to familiarize the research culture to the rest of our participants, we have kept these two sessions as well. So, my request to all, do have a voyage to Major University through this webinar as well as to BITS Milan in Goa in their very important or very high-end instrument laboratories. With this, I wish this webinar a success. And again, I welcome all the participants who are at present in Temple College online. I welcome also again Professor Mariama and Professor Rani for this webinar. Thanks a lot.
Thank you, madam, for sharing with us your thoughtful views. We will start with our first session, and the resource person for the first session is Professor Takahiro Maruyama, Department of Applied Chemistry, Meiji University, Japan. And Professor Takahiro Maruyama will be delivering a lecture on the topic Synthesis and Growth Mechanism of Carbon Nanotubes. Now I request Dr. Shashank Maldar to introduce our first resource person for the day.
Good morning to one and all. It is indeed an honor to have in our midst today Professor Takahiro Maruyama as a resource person for today's international webinar. Professor Takahiro Maruyama is currently working at Department of Applied Chemistry, Meiji University, Nagoya, Japan. He completed his graduation in the Faculty of Science at Kyoto University. Professor Takahiro Maruyama has completed his PhD at Kyoto University and postdoctoral studies at the University of Tsukuba and University of Ritsumeikan. Is the director of Nanomaterials Research Center at Meiji University and has published more than 180 papers in peer-reviewed international journals. Professor Takahiro Maruyama's present area of research includes the synthesis and characterization of nanomaterials. With this brief introduction, we welcome you, sir, to the international webinar, and I request you to kindly start with your lecture on synthesis and growth mechanism of carbon nanotubes. Over to you, sir.
Thank you for kind introduction. So, and good morning and good afternoon, everyone. So, thank you. Yes. So, I like to start my presentation. Yes, I am very pleased to be here, and Meiji University and DEMP College of Arts and Science concluded MOU in 2021, and now we are proceeding with academic and student interactions. So it's a great honor for me to have an opportunity to give a presentation in this international webinar on innovations and applications in materials chemistry. So the next slide, please. So before my talk about research, I'd like to introduce our university and Nagoya City. Major university is located in Nagoya. Can you hear me? Okay. Major university is located in Nagoya. Nagoya is located on the Pacific coast in central Honshu. Nagoya is the fourth biggest city in Japan, and over 2 million people make Nagoya their home. Nagoya is the industrial heart of Japan. Toyota, which is one of the biggest automobile manufacturers in the world, is a company in in this area. And there are many automobile companies near Nagoya City. Besides that, we can see old Japanese scenery in Nagoya, Nagoya Castle, Osu Temple, and so on. Next slide, please. Nagoya City is about 40 minutes by train from the Central Japan International Airport, also known as Centurea. Major University is located in the eastern part of Nagoya, about 40 minutes from Nagoya Station. So we can arrive at Major University from airport within 1 hour and a half. Next, please. Major University has 10 faculties. The number of total students is about 50,000. We have 3 campuses in the Nagoya City. Our laboratory is located in Tenpaku campus, which is the biggest campus among the 3. More than 10,000 students study on this campus. Next, please. So there are special professors in major universities. Our university has 2 Nobel Prize laureates. Professor Akasaki, he won the Nobel Prize in Physics in 2014 for the innovation of blue and white LED. His co-worker, Professor Amano, at Nagoya University, belonged to major university until 13 years ago. And Professor Yoshino, he won the Nobel Prize in Chemistry in 2019 for the innovation of lithium-ion battery. He gave a keynote lecture at the online symposium of Demp College in 2020. Next, please. Also, today's main topic, carbon nanotubes, were discovered by Professor Iijima, an emeritus professor of major university. He has won numerous awards in Japan and abroad. About 30 years ago, he discovered carbon nanotubes, which was prepared at major university by Professor Ando. He is also an emeritus professor of our university. Next, please. Major University has started 2 research projects supported by the Japanese government, private university research branding projects. Based on these projects, we have created 2 research centers, Nanomaterial Research Center and Optical Device Research Center. Professor Takeuchi is the director of Optical Device Research Center. And I am the director of Nanomaterial Research Center. So we are proceeding with the project related to nanomaterials and optical devices. Next, please. This is the outline of today's my talk. I would like to start the background, overview, and properties of carbon nanotubes, followed by talking about the motivation of single-wall carbon nanotube growth from platinum group metal catalysts. In the second part, I would like to talk about in situ Zapf analysis to investigate growth mechanism of carbon nanotubes. Finally, I would like to summarize my talk. Next, please. Carbon nanotubes are very small tubes which are composed of only carbon atoms. The diameters are typically only a few nanometers. When the number of wall is 1, they are called single-wall carbon nanotubes, SWCNT. If the number of wall is 2 or more, they are called multi-walled carbon nanotubes, MWCNT. Carbon nanotubes have been attracting much attention because they have various and tremendous properties. They show high carrier mobility, high electric current density, high thermal conductivity. Furthermore, they can be either metal or semiconductors, depending on their structures. So they are anticipated in many applications, such as in the field of electronics, nanotechnology, biotechnology, and energy materials, and so on. Next, please. Next slide, please. Yes. In the early stage, sports products and bicycles were sold where carbon nanotube resin composites were used to strengthen the shafts and frame structures. Also, synthetic composites were used for the vibration plates of high-end headphones and touch panels of Chinese companies' smartphones. But the market size was not so large. Next, please. In recent decades, carbon nanotube market is significantly expanding year by year. At present, the market of MWCNTs accounted for about 90%. This is because MWCNTs are used for additives in electrodes of lithium-ion batteries. Next, please. The polymer industry contributed towards more than 60% of the overall CNT market share and is expected to be the dominant application segment over the coming years. Now, many companies are producing MWCNTs and SWCNTs. Next slide, please. First of all, I would like to talk about the property of carbon nanotubes. Please, next slides. So one of the important structural parameters of an SWCNT is chirality. A sheet made of carbon atoms arranged in a honeycomb lattice is known as graphene. Chirality is how to roll up the graphene sheet to form tubular structures. To form a seamless tube, you need to take two of the hexagons in a graphene sheet and connect them. A vector connecting the top of two hexagons is called the chiral vector. The chiral vector C is defined as C equal NA1 plus MA2, where A1 and A2 are the basis vectors of a graphene sheet, and N and M are called chiral indices. Next, please. Depending on its chirality, a carbon nanotube can be both metal and semiconductor. That is, the electronic property of a carbon nanotube is determined by its chirality. Also, the band gap of semiconducting SWCNT is inversely proportional to its diameter. Stochastically, 1/3 of grown SWCNTs are metallic, while the others are semiconducting. However, selective growth of semiconducting and metallic carbon nanotubes are not realized yet. This impedes realization of carbon nanotube electronics devices. Next, please. So far, a few techniques have been reported to obtain SWCNTs with unique chirality. The methods are divided in two. One is the separation after nanotube growth. AIS2 group in Japan obtained SWCNTs with unique chirality by the Gell-Karam separation technique. This technique enables separation of single-wall carbon nanotubes with various kinds of chirality. However, after the separation, contaminants were contained, which are unfavorable for applications. Therefore, selective growth of single-wall carbon nanotubes with unique chirality is desirable. Peking University group attained selective growth of single-wall carbon nanotubes with unique chirality by using alloy catalysts, tungsten cobalt. And the German group reported selective growth by using organic molecule precursors. However, the obtained chirality is limited, or the yield was not high. So, selective growth of single-wall carbon nanotubes with unique chirality is still an important issue. Next slide, please. Next, please. At present, CVD, chemical vapor deposition, is widely used for carbon nanotube growth because CVD is suitable for mass production and cost-effective. In CVD, nano-sized metal particles are used to grow carbon nanotubes. They react with feedstock gas, such as hydrocarbon or alcohol gas, and decompose them to nucleate carbon nanotubes. In general, single-wall carbon nanotubes are grown at around 700 to 900 degrees C by CVD. Next, please. To grow carbon nanotubes by CVD, iron group elements such as iron, cobalt, and nickel are widely used as catalysts. This is because the number of d electrons and their energy levels are related to decompose the feedstock gas. The metals with a small number of d electrons have high reactivity with feedstock gas. This leads to formation of metal carbides, which sometimes results in the deactivation of catalyst. On the other hand, metals with 10 d electrons, that is, completed filled d quartz, such as copper, silver, and gold, have low activity with feedstock, so they are not suitable to grow carbon nanotubes. Next slide, please. The melting points of iron, cobalt, and nickel are about 1,500 degrees C, which are much higher than the growth temperature of carbon nanotubes. However, catalyst particles are nano-sized, which induces the depression of melting points by Gibbs-Thomson effect. As a result, aggregation of catalyst particles occur, which leads to the enlargement of nanotube diameter. This causes the enlargement of carbon nanotube diameter, and both diameter and chirality distribution became inhomogeneous. So it is important to suppress the aggregation of catalyst particles. Next, please. To suppress the aggregation, we focused on platinum group metal catalysts. They have 6 to 9d electrons and show activity suitable for carbon nanotube growth. In addition, their melting points are near or higher than 2000 degrees C and much higher than those of iron group elements. So the aggregation of catalyst particles would be suppressed. Next slide, please. Yes. Next slide, please. This shows the experimental procedure for carbon nanotube growth with platinum group element group metal catalysts. We formed catalyst particles on silicon dioxide silicon substrate by the pulsed arc plasma deposition. It formed nano-sized metal particles on the substrate. So could you click the slide? Yes. So this this shows TM image of catalyst particles. So the sizes are from 1 to 3 nanometers. To grow single wall carbon nanotubes, we used cold wall type CVD system using ethanol gas as feedstock. This method is called HCCVD, alcohol catalytic CVD. And our system is a gas source type. So the ethanol gas was supplied through a thin nozzle onto a substrate surface in a high vacuum chamber. Therefore, minute control of feedstock gas supply is possible. Next slide, please. The left figures show SEM and TEM images of the sample grown at 700 degrees C. This sample was the carbon nanotubes grown from platinum catalyst. So wave-like structures were seen on the substrate, and single-wall carbon nanotubes were observed in TEM image. The right figure shows PL, photoluminescence mapping of grown SWCNTs. PL mapping can determine chirality of semiconducting carbon nanotubes. Next slide, please. We also performed Raman measurements and determined chirality of grown nanotubes. These show the chiral maps of single-wall carbon nanotubes grown from platinum catalysts at 700 and 400 degrees C. Also, both semiconducting and metallic carbon nanotubes are present. The diameters were distributed below 1.1 nanometer. That is, small diameter single-wall carbon nanotubes were grown from platinum catalysts. This would be due to the suppression of aggregation of catalyst particles. As the gross temperature decreased to 400 degrees C, the chiral distribution became narrower and the diameters became smaller. Next slide, please. These show comparison of nanotube diameter distribution between platinum and cobalt catalysts. The diameter distributions were estimated by RBM peaks in the Raman spectra, measured with 3 excitation wavelengths. Irrespective of the excitation wavelengths, the nanotube diameters from platinum catalysts were smaller than those from cobalt catalysts. So we confirm that the nanotube diameters from platinum catalysts were smaller than those from cobalt catalysts. Next slide, please. We also performed a single-roll carbon nanotube growth by ACCVD using iridium catalysts. Raman measurements showed that, like platinum catalysts, SWCNT diameters were distributed below 1.1 nanometer. It should be noted that vertically aligned single-wall carbon nanotubes, so-called nanotube forests, were formed on SiO2 silicon substrate. This means that iridium catalysts are highly efficient to grow single-wall carbon nanotubes. The lower figure shows the diameter distributions of single-wall carbon nanotubes grown from iron, cobalt, and iridium catalysts. Previously, vertically aligned single-wall carbon nanotubes were grown only from iron and cobalt catalysts. However, the diameters of grown nanotubes were distributed from 1.0 to 2 or 4 nanometers. In contrast, our results showed iridium catalysts are effective to grow small diameter single-wall carbon nanotubes with high efficiency. Next slide, please. Next, please. Thank you. Please back to previous slide. Yes. Recently, we also succeeded in growth of vertically aligned and small diameter single-wall carbon nanotubes on a stainless steel foil using iridium catalyst. This method will be applied for mass production of small diameter single-wall carbon nanotubes. Next, please. We also performed single-wall carbon nanotube growth using osmium as catalysts. In this experiment, osmium were deposited on SiO2 silicon substrate by using an osmium coater, which is widely used for the sample preparation of SEM observation. Then SWCNT growth was performed by ACCVD. Next slide, please. Using osmium catalysts, we succeeded in vertically aligned SWCNT growth. Next slide, please. So we succeeded in vertically aligned SWCNT growth. Although the length was short, about 50 nanometers. But the diameters were below 1.1 nanometer, which were similar to those from platinum and iridium catalysts. So we demonstrate that platinum, iridium, and osmium, so platinum group elements in period 6 are suitable to obtain small diameter single wall carbon nanotubes. Next slide, please. Next, I would like to talk about single wall carbon nanotube growth at low temperature. So far, several groups reported SWCNT growth at low temperature by CVD using iron or cobalt catalyst. Many groups reported SWCNT growth at 400 degrees C. Among them, University of Cambridge group attained SWCNT growth at 350 degrees C by thermal CVD. Next, please. Here, we use rhodium as catalyst to perform low temperature growth. Rhodium catalysts were deposited on Al2O3 SiO2 silicon substrate. Then SWCNT growth was performed by HCVD. Next, please. This shows the relationship between the growth temperature, the ethanol pressure, and CNT yield. CNT yield was roughly estimated from the intensity ratio of G-band peak to silicon phonon peak in Raman spectra. The CNT yield decreased as the growth temperature became lower. It should be noted at 550 degrees C, the nanotube yield became maximum at 1 times 10 to the minus 3 Pascal of ethanol. But at 460 degrees C, the yield became the highest at 1 times 10 to the minus 4 Pascal. This indicates that the optimal ethanol pressure decreases as the growth temperature was reduced. This means precise control of ethanol gas pressure is necessary to grow SWCNTs at low temperature. Next slide, please. This shows the Raman spectra for SWCNTs grown from rhodium catalysts at low temperature under the optimal ethanol pressures. Both RBM and G-band peaks were still observed, even at 320 and 270 degrees C. That is, single wall carbon nanotubes grew below 400 degrees C. Next slide, please. This figure summarizes low temperature growth of single wall carbon nanotubes, including previous studies. We succeeded in single wall carbon nanotube growth below 300 degrees C using rhodium catalysts. In this figure, the vertical line shows GD ratio in Raman spectra, which corresponds to carbon nanotube crystallinity. As you can see, the GD ratio of carbon nanotubes from rhodium catalysts is relatively large, even though the growth temperature was below 400 degrees C. This indicates rhodium catalyst is effective to grow single carbon nanotubes at low temperature. Next slide, please. This is a summary of the first part. We succeeded in small diameter single carbon nanotubes using platinum group metals as catalyst. And vertically aligned small diameter nanotubes were grown from iridium and osmium catalysts. And we fabricated a vertically aligned single carbon nanotube layer on a stainless steel foil using an iridium catalyst. Also, we succeeded in low temperature growth using rhodium catalyst below 300 degrees C. Next slide, please. So next, I would like to talk about in situ Zuss analysis for catalysts during nanotube growth. Next, please. So as I mentioned, in CVD, nano-sized metal catalysts react with feedstock gas at high temperature to grow carbon nanotubes. In this process, the physical and chemical states of catalyst particles are considered to affect the nanotube structure. The electronic states of a single carbon nanotubes are determined by their structure, such as diameter and chirality. Therefore, to understand the state of catalyst particles is important to control the structure of an SWCNT. Next, please. So in particular, it has been pointed out that growth mode is determined by the chemical state of catalyst particles. French group reported if catalysts are carbides, the tube diameter is smaller than the particle size. That is called perpendicular mode. On the other hand, if the catalyst particles are metallic, the tube diameter is almost the same as that of particle size. That is a tangential mode. This means the chemical state of a catalyst particle determines the growth mode. Next, please. So far, several studies about in situ analysis for carbon nanotube growth have been reported using TEM and XPS. However, basically, TEM and XPS are analysis techniques under high vacuum. Therefore, they are not suitable for in situ analysis under the typical growth condition in CVD. Also, it is difficult to use TEM for observation of nanotube growth with ethanol gas. Next, please. So in this study, we used X-ray absorption fine structure ZAFS measurements for in situ analysis. ZAFS is an experimental technique to measure X-ray absorption spectra. The measurement of fine structure near the absorption edges, that is Zane's region, provides information about the balance state of target elements. Also, analysis of the fine structure far above the absorption edge, that is exact region, provides information about structure. ZAFS is applicable for analysis at high temperature and high pressure. Therefore, ZAFS is suitable for in situ analysis under the conventional growth condition of carbon nanotubes. Next, please. So, in situ surface analysis was performed at Aichi Synchrotron Radiation Center, Japan. Aichi Synchrotron is located at northeast of Nagoya. It is about 15 kilometers away from our university. It takes about 40 minutes by car. Next, please. This shows the experimental procedure about the sample preparation for cobalt catalyst. Cobalt acetate, tetrahydrate, boron nitride slurry, and boron nitride powder were mixed and sintered. Then they were molded to form cobalt BN pellet. In situ surface analysis was performed at beamline 11S2 of Aichi Synchrotron Radiation Center using a transmission mode. This shows schematics of experimental apparatus. We set a small CVD system at the beamline for in situ surface analysis. Next slide, please. This shows temperature sequence. The gross temperature was 800 degrees C. After the furnace temperature reached 800 degrees C, ethanol gas was supplied to grow carbon nanotubes. Next, please. So after in situ surface measurement, we analyzed surface spectra in the exhaust region. So please click the slide. Could you click to show next figure? So after background subtraction and Fourier transform, we obtained radial structure function RSF. Yes. Furthermore, by curve fitting analysis, we determined local structure of target element, such as coordination number and bond distance. So we can get information about local structure of target element. Next, please. The left figure shows the spectra of the as prepared cobalt BN sample. For reference, the Zeus spectra of cobalt foil and cobalt compounds are shown as dotted lines. As you can see, the surface spectrum of the as prepared sample was similar to cobalt acetate. This indicates the balance of cobalt catalyst. Cobalt is about 2. The right figure is RSF, radial structure function. The cobalt oxygen peak is dominant. This confirms the as prepared sample was mainly composed of cobalt oxide. Next slide, please. These show Zaf's spectra during heating to the gross temperature 800 degrees C and during carbon nanotube growth. As the temperature rises, the peak at the absorption edge decreased. This indicates reduction of cobalt catalyst. After ethanol supply for single-wall carbon nanotube grows, the spectral shape changed a little, and the peak intensity decreased. Next slide, please. The left figure shows RSF during single-wall carbon nanotube growth. After ethanol supply, the dominant peak shifted to cobalt carbon position. This indicates formation of cobalt carbides. To investigate chemical state in more detail, we estimated coordination numbers of cobalt carbon and cobalt oxygen bonds by the curve hitting of RSF. So the right figure shows the variation of the ratio of coordination number. So before ethanol supply, cobalt catalysts were mainly cobalt oxide. But after nanotube growth started, cobalt catalysts became mixture of cobalt carbide and cobalt metal. Next slide, please. After in-situ Zapf analysis, we performed Raman, TEM, and SEM to confirm nanotube growth. In Raman spectra, both RBM peaks and G-band peaks were observed, and TM observation also confirmed growth of single carbon nanotubes. So we confirmed during in-situ Zapf analysis, single carbon nanotubes were grown. Next slide, please. We also performed in-situ Zapf analysis for other elements, iron, nickel, iridium, and platinum catalysts. These show RSF and the ratio of coordination numbers during single-wall carbon nanotube growth from iron and nickel catalysts. In the case of iron, the catalysts were mainly oxides, but after ethanol supply started, the ratio of iron carbides increased. For nickel catalysts, they were reduced to metallic during temperature rise. And the chemical state of nickel was mainly metallic, but slightly carbonized during nanotube growth. Next, please. These show RSF and the ratio of coordination numbers of iridium and platinum catalysts during carbon nanotube growth. In the case of iridium and platinum, the chemical states were almost metallic. Next, please. These show growth process of single-wall carbon nanotubes from iron, cobalt, and nickel catalysts. In the case of iron group elements, catalyst particles became carbide during single-wall carbon nanotube growth. However, the degree of carbonization was different. Iron was highly carbonized, while nickel was slightly carbonized. Next slide, please. Next, please. In contrast, the platinum group elements, iridium and platinum, the catalyst particles were metallic during nanotube growth. It should be noted, TEM observation showed tangential growth mode for nanotube growth from iridium catalysts. This result is consistent with previous prediction. Next, please. So previous in situ TEM analysis showed that cobalt and iron catalysts became carbides. Our results by in situ Zapf analysis under the conventional growth condition was consistent with them. However, we observed nickel catalysts were slightly curved under the conventional growth condition. Also, we found that platinum group metal catalysts became metallic during nanotube growth. This is the first observation for platinum group metal catalysts using in situ analysis. Next, please. This summarizes the ratio of metal and carbide for each catalyst metal during nanotube growth. The lower table shows carbon solubility and formation energy of interstitial carbon for each metal. As you can see, as the bulk carbon solubility becomes larger and the formation energy of carbides becomes lower, the degree of carbonization increases. Next, please. So it should be noted for cobalt and nickel catalysts, the degree of carbonization was higher than the bulk solubility. It is well known the melting point of a metal nanoparticle is depressed as the particle size decreased to nano size. It has also been pointed out that carbon solubility increases with the decrease of particle size. So we consider that such a nano-sized effect occurred for catalyst particles, which results in the increase of carbon solubility. Next, please. Also, I'd like to mention the theoretical simulation about metal nanoparticles during single-wall carbon nanotube growth. Amara calculated distribution of carbon atoms in nickel catalyst particle during single-wall carbon nanotube growth. They demonstrated that carbon atoms were mainly distributed near the catalyst surface, and single carbon nanotubes were grown from the surface carbide layer. This means that carbon concentration is high in the near surface region. We consider such a situation might occur for nickel catalyst. As a result, carbon concentration of nickel and quartz catalysts were higher than those of bulk states. Next, please. So finally, I'd like to summarize my talk. So thank you for your kind attention. This is a acknowledgement and financial support for this study. I'd like to thank my students. Thank you for your kind attention. Thank you very much.
Thank you, Professor. I apologize for that. Thank you, Professor Takahiro Maruyama, for sharing with us your research outcomes and providing us with valuable insights into carbon nanotubes. I
Thank you
request
very much.
all the participants to kindly post their questions in the chat box, if any, or you all can directly unmute the mic and ask the questions to the speaker.
Hello, Professor.
Hello.
Hello, I am Dr. Rane. I enjoyed the talk of yours. It's highly technical. Just a small doubt for me. Supposing in a cobalt substrate catalyst, if there is a cobalt and oxide and cobalt carbide and cobalt cobalt linkage is there. Supposing more percentage of cobalt oxide is there, what would happen to the growth of the nanotube?
We think co- the catalyst particles which grow carbon nanotubes are mainly composed of carbide and cobalt metal. So,
Yeah.
so cobalt, yes. So we saw cobalt oxide, but so some particles were not completely reduced to metallic.
Metallic.
So such a particles
Yeah.
would be still oxide during natural growth.
Okay. Thank you very much. Yeah. Thank you very much.
Thank you. Thank you for question.
Professor, we have another question from Mrs. Varsha Virjinkar. Any other solvent other than ethanol, whether it can be used for carbonization?
Yes. So, generally, ethanol and hydrocarbons such as acetylene C2H2 or ethylene C2H4 are widely used, or carbon monoxide. So, we think the reaction process processes are different between the feedstock gas. So, I would like to investigate other feedstock gas, such as acetylene, in future.
Thank you, Professor, once again for accepting our invitation and for delivering us with such an informative lecture.
Thank you.
Thank you, Professor.
No.
Thank you, Professor.
Thank you very much. Okay.
Yeah. The nice
Thanks a lot, sir.
No, thank you very much.
Thanks
Thank
a
you.
lot for joining.
Yes.
Yeah, thanks a lot for joining as well as giving a very technical session, a very informative one. Okay, and a good insight into the use of various platinum, osmium, and iridium use in this synthesis. Thank you.
Yes.
Thanks a lot.
Thank you. Thank you very much for inviting me.
The next resource person for a session is Professor K.S. Rane, Adjunct Faculty, Gokte Institute of Technology, Belgaum, India. And Professor K.S. Rane is going to deliver the lecture on the topic Photocatalytic Remediation of Emerging Pollutants. I request Mrs. Deepa Odi to introduce the guest speaker for this session.
Thank you, Deepika. Good morning, everyone. I take this privilege to introduce the speaker for the second session, Professor K.S. Rane, who has been the former head at the Department of Chemistry and Dean of Faculty of Natural Sciences at Goa University. Professor Rane has pursued his PhD from IIT Mumbai in the year 1976 and further pursued postdoctoral degree from IIT Madras, Pune University, Germany, UK, and USA. Sir has been the teaching faculty at Gokte Institute of Technology, Goa University, visiting professor at Washington University, USA, and presently the founding coordinator of PG department at Rani Chennamma University, Belgaum. His teaching and research experience are in the areas of inorganic chemistry and material sciences. Professor Rani has been honored with many fellowships: the DART German Fellowship, CSIR Visiting Scientist Fellowship, University of Manchester Institute of Science and Technology Fellowship. Sir has completed 3 international and 10 national projects and guided many PhD students and MSc dissertations at Goa University. Professor Rani has 52 publications in the international and national journals and more than 250 conference proceedings to his credit. Professor Rani is presently the principal investigator for the project Photocatalytic Degradation of Pharmaceutical Active Products, Dyes and Pathogens in Water due to the sudden surge of waste in COVID pandemic period. Today, Sir will be addressing on the topic photocatalytic remediation of emerging pollutants. Many of us have been fortunate and are blessed to be his students at the Department of Chemistry at Goa University. I take this opportunity on behalf of the Department of Chemistry to welcome Professor Rani at Dempe College on this virtual platform and request Sir to kindly take over the session. Thank you.
Thank you very much, Dr. Audi. Thank you very much. I think Varsha can project out my talk. Yeah, good morning. And thank you very much again for introducing me. It is my pleasure to deliver a talk on photocatalytic remediation of emerging pollutants. Yeah, next slide, please. Yeah, I have organized my talk under these headings: the overview of the water pollution in India in particular, established processes of drinking water treatment, concern in organic carbon removal, uh, advantage of the advanced oxidation process in the mineralization of organic materials and enhancing the disinfection, metal oxide semiconductors as a photocatalyst, mostly visible light sensitive, effectiveness of the INO rejects and their beneficiated products in the degradation of the organic materials and emerging pollutants, and inference. Next slide, please. Well, water, the elixir of life. Man has been searching for an imaginary elixir of life for ages, but the true medicine is the simple water. Alas, it is not anymore. Next slide, please. As you know that in the 2018 Expo 5th Water, India is found to be occupying around 2% of the world's land area, represents around 16% of the world population, 15% of the world livestock, but it has just 4% of the water resources of the world. In India, 80% of the surface water is polluted. 75% of the water pollution is from domestic sewage. And wastewater treatment in India is just 31% of the urban water, wastewater, and 37% of the urban sewage. Next slide, please. A global scenario is something very sickening here. The water quality facts that 2.4 million live without any form of sanitation. 90% of the sewage in developing countries is discharged untreated directly into the water bodies. Every day, 2 million tons of sewage and other effluents drain into the world's water. Industry discharges an estimated 300 to 400 megatons of waste into water bodies every year. Next slide, please. Coming to Indian standard of drinking water, maybe you are all very much familiar with that one. There is a stringent condition that pH should not be more than 8.5, not relaxable. The other chloride, fluoride, nitrate should not be more than 45 ppm, not relaxable. Sulfate 200 ppm. And you can see here, iron should not be more than 0.3 ppm. It's not relaxable. It should not be more than 0.3 ppm. Copper 1.5 ppb level. It should not be more than that one. So, but coming to the microorganism, that is a BOD, it should be less than 5. And COD is a measure of the organic, not mentioned in the Indian standard. And in fact, I am going to deal with the organic pollutants only, though it is not given in the Indian standard. As you know that India is doing very good in treating water, even for the rural habitations. There are, in the rural habitation, there are the toxic elements like arsenic, chlorine, iron, nitrate, heavy metals, and salinity. They are there, and most of these habitations have been well connected by the Indian government, and they are now doing a very good job of giving the pure water for the rural people. Next slide, please. Next slide, please. Yeah, Government of India is taking all steps to contain water pollution, mainly the inorganic. There is no problem about the inorganic. Enough processes are there to remove the inorganic pollutants. Next slide, please. But the organic pollutants are rather difficult to manage, though there are some very expensive adsorption techniques which can, at the most, remove 60% of natural organic carbon and 20% of dissolved organic carbon. Some of the organics are carcinogenic, as you are all aware of that one. Next slide, please. Of late, emerging pollutants are creating a very difficult task in controlling the water bodies. Next slide. Emerging pollutants are pharmaceutical active products, antibiotics, drugs, steroids, endocrine disruptors, hormones, industrial additives and chemicals, and microbeads, microplastics identified as dangerous to the environment and consequently to the health of the living organism. You can see that these emerging pollutants have not been regulated under national or international legislation, hence posing a greater risk to our livelihood. Next slide, please. Most common water treatment processes are filtration system. You're all familiar with those things. Water softeners to remove all the inorganic elements. But disinfection is commonly done with the chlorine, and chlorine is worldwide it is used. And there is also physical disinfections done by ultraviolet radiation, electron radiation, and heat. These are all the most common treatment processes. Next slide, please. Although chlorination is widely used, it has several disadvantages, such as formation of disinfection byproducts and being ineffective against some types of microbes. There are undesired compounds that may be produced from the chlorine reacting with the organic matter. Since I have been treating with the organic pollution, so one should know that the chlorine can directly react with the organic matter present in the water, such as humic acid, fulvic acid that generated from the decay of organic matter. The compounds of most concern right now are the trihalomethanes and haloacetic acids. Hence, organic matter in water needs to be controlled. Therefore, chemical oxygen demand, a measure of organic matter, requires to be very low. As I said, in the Indian standard, it is not given what should be the minimum the desired COD in the drinking water. It is not mentioned. If organics are not controlled, microorganisms thriving on organic nutrients would consume dissolved oxygen to produce their food. Therefore, the biochemical oxygen demand, a measure of microorganisms, should be very low. Both BOD and COD eventually decrease the dissolved oxygen content in the water, making it unsafe to living organisms as well as animal and bird kingdom. So one has to very careful about the COD. Of course, BOD people are making the enough efforts to remove the BOD level, bring it to a manageable level. But COD, as I said, is not taken that much care. Next slide, please. So how to investigate the degradation of organic, thereby provide remedial measures? There are very few processes, as I said. It is found that the traditional wastewater treatment plants remove less than 50% of pharmaceutical waste. It means tackling such emerging problems is not an easy job. Next slide, please. Techniques such as expensive adsorption and membrane technology are used world over, but such poor countries cannot afford to have such a process. Biological treatment and advanced oxygen processes are now taken very seriously, and these are all the tertiary methods to deal with such a nuisance of emerging pollutants. One can't afford to have all these processes like advanced oxygen processes, but in the laboratory level and in a small way, one can make use of advanced oxygen processes for treating the organic matter as well as microorganisms. One that has a promise is an advanced oxidation process. Next slide, please. Advanced oxidation processes are, one can directly send ozonization, H2 ozone and H2O2 ozone, and UV light and H2O2, TiO2, that is catalyst, and UV light, H2O2 and catalyst, photophenton reactions. They're all very advanced procedures. One cannot manage to go for such treatment for large quantity of water, which is really released by the municipality. So it's very difficult. So hence we need to think about something, a different process, and that is what is some of the people are thinking about, a photocatalysis. We are discussing here the photocatalytic processes to mineralize the organic and disinfect the microorganisms in the wastewater. Next slide, please. Photocatalysis mainly there is a generation of reactive oxygen species by irradiating the semiconducting oxides, metal oxides, and you can see that when the electromagnetic wave is impinged on the semiconductor, electrons are excited to the conduction band and holes are formed at the valence band. As there is an adsorbed oxygen present in the semiconductor, which will react with the electron thus released, forming superoxide radical. As well, the surface hydroxide or surface moisture present in the semiconductors reacts with the holes formed and reactive hydroxyl radical is formed. And if you see the various oxidation potentials of the various species which are used in oxidation, fluorine is having the highest oxidation potential, and atomic oxygen is around 2.4, ozone has got 2.07, hydrogen peroxide is around 1.7, permanganate, which normally use 1.68, chlorine is just 1.36, and oxygen molecule has got potential of 1.26. Considering all those things, fluorine is the best oxidation, has got very good potential. But if you look at the hydroxyl radical thus produced on the semiconductor, is equally very close to the fluorine and better than all other oxidants. So people are thinking about such advanced oxidation processes in which reactive oxygen species are formed easily at room temperature only by just evaporating the semiconductor oxygen. Even such hydroxyl radicals can break open the so-called stubborn benzene. Otherwise, it's very difficult to break the benzene. So it means benzene can be mineralized by hydroxyl radicals. Next slide, please. We have been working in the laboratory level how to break the organic molecules. So normally people use the methylene blue as a target material, as a model material. And methylene blue as such, if it is uh, exposed to sunlight, it hardly degrades. You can see here, even at 24 hours, there is no much degradation taking place. The moment you put some catalyst, metallic catalyst, you can see the degradation taking place almost 80% to 90%. The various catalysts can be used, which you can see that the degradation can be done by adding different catalysts. For example, the titanium oxide, molybdenum oxide, and digoside itself. Yeah. So it means that methane blue, such a huge molecule, can be broken down at ordinary temperature on the semiconductor under sunlight. Just a sunlight irradiation is sufficient to degrade the such a molecule of methylene blue. It means organic molecules, if they are present in the water, can be degraded if you properly manage to have a catalyst which can do the job of that one. Next slide, please. Methyl red also can be degraded, or you can see that decolorization can be done with in the presence of various catalysts, molybdenum oxide, titanium oxide, and all those things. Or in a simple sunlight, also it degrades, not to that extent, but the degradation is higher in the presence of the catalyst in sunlight. Next slide, please. Methyl orange, for that matter, also can be decolorized in the presence of various catalysts. In the sense, in the advanced oxidation processes, one uses the metal oxides, and normally they are energized with the electromagnetic radiation. In our case, we have just energized with the simple sunlight, and we can see that there is a degradation taking place. It means one can make use of semiconductors for mineralization of the or decolorization. I'm using the word mineralization as well as decolorization. Now the thing is that decolorization means it is not mineralized totally. Mineralization means the total organic compound should go to CO2 and H2O. That is the simple friendly products. Any organic matter for that matter should get mineralized into carbon dioxide and the water. If that happens, it means that we are easily removing the organic matter present in the water by simple the metal oxide and the sunlight. Next slide, please. Next slide. Well, I have also used some caffeine. Yeah, caffeine also can be mineralized by using various catalysts. Various catalysts can be used and one can mineralize it. Next slide, please. We have used paracetamol. Since I have a project, as the introducer said about my project in the medical college, so I'm just thinking about some of the pharmaceutical products, whether they can be degraded or mineralized.
Sorry to interrupt. Sir, you are not audible.
Sorry, there was some disruption here. Hello? Yeah?
Yes, sir, you are audible now.
There was some disruption. Sorry for that one. Okay, next slide, please. Well, we have also used pharmaceutical products like prednisolone, which is widely used, and we do find that catalyst can degrade the prednisolone, whereas the prednisolone degradation has been studied in the literature. You can see that it requires the alkali to degrade 100%. So we cannot put in the water alkali to remove such the pharmaceutical product. One the acid cannot degrade the prednisolone, whereas H2O2 can degrade around 60% or so. Simple sunlight cannot degrade. It is almost 12% degradation takes place. Heating also will not do the job of degrading. It means the pharmaceutical products are such a stubborn things. One has to remove those things, even they are in the ppm level or ppb level. And we do find that with the catalyst, we can remove almost 60% of the prednisolone with the simple catalyst. So it means a metallic semiconductors have got some effectiveness to degrade the pharmaceutical products, and that is the reason why I have chosen this particular project for uh, uh, understanding the degradation of uh, the pharmaceutical products. Next slide, please. Exhaustive literature is there on the photocatalytic degradation of organic dyes, as almost all dyes are non-biodegradable, creating problem in water treatment processes. Among the dyes, the methylene blue is the most widely studied. Normally, people begin with that one, then they extrapolate that work for any other organic material. So we are just exhaustively studying the methylene blue in our studies. The next slide, please. Now you can see that methylene blue is blue in color. Yeah, and as you say that in the sunlight doesn't degrade, the color remains. But when you continue exposure of the sunlight for more than 60 days, you can see that complete decolorization has taken place of the methylene blue. Whereas same methylene blue is kept in the dark, there is still methylene blue color remains there. And if you see the total organic carbon removal in the sunlight, it is just 14%, though it is colorless, and it looks that as it degradation has taken place, but the total organic carbon removal is just 14. It means the remaining 85% is the organic matter is still there, but it's a colorless. So people may think that I have removed the color. It doesn't mean that we have removed the organic part of that one. There are some organic parts still remaining in the methylene blue. So normally in the literature, we study the methylene blue degradation for 24 hours, then study the kinetics and all things. Then we say that our catalyst is the best one, all those things. But in fact, the organic matter is still there in the methylene blue. In the dark, you can see just 7% organic matter is removed. When I put the catalyst in sunlight, you can see that there is a tremendous increase in the TOC removal. It means molybdenum oxide is removing the methylene blue. Almost 70% methylene blue is degraded, but there is still around 35% organic matter is there. We don't know what is it. Similarly, the molybdenum oxide prepared by a different method shows only 40%. It means catalyst also makes a lot of difference in degrading the organic matter. When I use another molybdenum oxide prepared by some other method, it removes almost 42% of the organic. It means not only the catalyst, the preparation of the catalyst also very important while dealing with the degradation of the any organic matter. Here in this case, I have used only the methylene blue. Same way, when I use the iron-based catalyst, you can see that the methylene blue color has changed to something yellowish. It is due to the iron present in that one, and we see that around 58% of the organic matter is removed. Whereas another preparation of the iron, it removes around 71%. It means even in the iron catalyst, if you tailor properly the metal oxide, you can do the lot of difference in degrading the any organic matter for that matter. And you can see that there are almost 71% is removed when there is a FeOH type of the compound is present. If I take simple iron ore, which is there in the plenty in Goa, and I have been using that one, and simple iron ore removes 72% of the color it removes, and also organic matter. And simple iron oxide can remove 64%. It means there is a lot of role of this catalyst in removing the organic matter present in any dye or any organic present in the water. Now you can see the very funny thing is that very rarely you see in the literature people working in the dark condition. So idea is that when we are using any catalyst for in the advanced oxidation processes, if the daylight only if it is effective, we have large hours in the dark, and the catalyst has no meaning in the night time. So I want to see whether we can make use of the catalyst day and night, so that efficiency can be increased, load of the catalyst can be decreased. So we are looking for the catalyst which can work even in the dark time, dark conditions. So we see that in the dark condition, though simple methylene blue has TOC removal is 7%, but in the presence of catalyst, it has increased to 32%. And another catalyst, it is just 14%, 38%. And here you can see that the FeOH type of catalyst can. So now the real question of what is happening in the dark conditions. Whether you call it as a photocatalyst means that there should be light to irradiate on the semiconductor so that electron holes may be formed. So what is happening in this particular, this is the big question for me. I have been working on that one, and I invite the question from the audience. Next slide, please. Well, for a simple laboratory purpose, the students who want to work on that one, you can see that a methylene blue, when it is just exposed to sunlight in the 24 hours, there is hardly any much decolorization taking place, the degradation taking place. If I use the catalyst, there is almost 70 to 80% the degradation can be seen on the UV visible absorption spectroscopy. Now, after 60 days, as I have seen that most of them are colorless, and most of them have removed, most of the lambda maximum has come to almost 98% decrease. So it says that there is a degradation taking place. But same thing in the dark condition, you can see still methylene blue is intact. So for a simple study in the laboratory, where you can use a simple UV visible spectroscopy and find out what is happening with the any dye or any other organic matter for that matter. But then what is left here? what is left? Even if it is 80% color removal and some 70% of the uh, total organic carbon is removal, what is left behind, it, unless we tell about that one, who knows? Maybe the whatever left here is much more toxic than what we are thinking about the methylene blue or any other pharmaceutical product. So we need to know the what is there in the degraded product. The next slide, please. Next slide. Yeah. Okay. As you see that organic carbon removal is indication of the methylene blue degradation, or for that matter, any organic matter. Any organic matter, if TOC is removed, it means the organic matter is degraded. And you can see that degradation is more in the sunlight and less in the dark condition. Next slide, please. Well, now people can also study the COD, conductivity, sulfate ions present, pH, nitrate, chloride ion, and this will also give the rough idea about the what is happened in the dye, or for that matter any organic matter in the water once you have used the semiconductor and irradiated with the sunlight. You can see that organic carbon COD is removed maximum. So COD is removed maximum in the sense, so lot of organic matter can be removed in the presence of catalyst. The other things, pH and all those things, will give us the rough idea about the what is in the water. And COD removal is more, so that COD is the measure of the organic matter. So if I use any organic matter and if I use any catalyst, and if I study these parameters, I can see that organic matter is being removed fully or partly. It gives the indication that some of the organic matters is being removed by us by using the semiconductor. Next slide, please. Yeah, so you can see here the pH of the methylene blue, yeah, almost remains same by using various catalysts. It means then you can see conductivity also there is a variation. Sulfate ions also there is a variation, and you can see COD removal also can see that maximum in a particular zinc oxide or something. So various different semiconductors can be made use and think about best possible catalyst for the removal of the organic matter. So in the sense, an advanced oxidation process in which we are using the metal oxide semiconductors have got some efficiency to remove the organic matter. This is so far so good, as you think that we are able to remove the organic matter from the wastewater or any other water we are thinking about making use of it. Next slide, please. The catalyst seems to be very effective in degrading organic moiety in ordinary sunlight and even in the dark condition. However, the study does not reveal what is the fate of the organic and what degradation products are formed. And this is a very important. Unless we the tackle this particular thing, we cannot say that our catalyst is a good one or something. Who knows? The degradation products themselves are much more toxic, and if we have not noticed that one, we are giving the water having all these poisonous materials. And this needs some deep study, say HPLC, LCMS, and NMR. Next slide, please. Well, we have done some HPLC and LCMS studies on our methylene blue degraded products. You can see that in methylene blue, when it is degraded by exposing to sunlight, as we said, 14% TOC has been removed. So remaining 85% is organic moiety. Yeah. So we try to see those organic moiety by HPLC as well as LCMS. Yeah, and we find so many products formed. This all just matching with the mass by shed whatever we observe and matching with the plausible structures present in this particular format. But you can see there are so many products are there. Who knows whether this is much more toxic or this is toxic? Unless we tell this one, we cannot say that the semiconductor is a good in degrading. And in this case, it's not degraded. It is hardly 14% degradation taken place. Whereas here 7%, and you can see that still lithium blue is intact. It means LCMS study is okay for us. But other products we are just matched with the directory, and until we confirm their structure, we cannot give any mechanism for the degradation process. Next slide, please. Now, as you see that the in sunlight and in the dark condition, we have seen that many catalysts are showing the TOC removal to say 64%, 32, 40, and also fine. And if you see in the LCMS, there are so many products are there. Yeah, in the dark condition, lithium blue still remain there, and other products are found. Unless you identify them, I cannot say the literature also it doesn't tell us that, oh, this catalyst is good for removal of all this one, or total mineralization taken place. Means total mineralization will lead to carbon dioxide and H2. But we have seen that there are still some products are there, maybe in a very, very low concentration, and if they are much toxic, then our process may not be suitable for removing this organic matter present in the water. So it's a big question mark. So how to go ahead in identifying the different the products present in the water, and more already they are in the ppm level or ppb level. I don't think anybody can suggest me about the any other method, NMR or something, how to do. I don't know about that one, but our main aim is to bring down the organic matter present in the wastewater, especially in the medical premises where the lot of medicines are used by the patients, and the whole thing is going into the drain, and that then it is entering to the STP, the sewage treatment plant, and after sewage treatment plant, whatever is coming, still there is organic, because there is no process to remove the organic matter. So we are releasing that water from the STP to the nearby garden that percolates in the ground, and nearby wells will have that organic matter. So people may be having contaminated water around that one. So how to remove all those things? The next slide, please. We have used some other catalysts also, as you have seen. The best catalyst, I feel that the FeOH. Yeah, for my study, it is only 2-3 products are remained there. But even then, unless I confirm their presence, I cannot suggest the catalyst for the removal of any of these pollutants, organic pollution in the water body. So the question remains, though advanced oxidation process has potential to degrade the organic matter, good, because no other process is there to remove the organic matter. As I said, only 60% or only 20% can be removed by all advanced processes. Only advanced oxidation process has got better possibility to remove organic matter. But the question still remains that how to identify the products formed in the water, and if those products are much more toxic, I don't know whether we have to suggest such a method to the authorities or not. Next slide, please. So in general, dyes and pharma products degrade in the presence of catalysts. So theory suits to us to remove the organic products, organic pharma products. Dye degradation in the dark condition is low, as you have seen, and showing slight fading of the color, but in sunlight, though the color is vanished, the TOC removal is just 40%. My question is that why there is a degradation taking place in the dark condition in the presence of catalyst also. Metal oxide semiconductor show enhanced degradation in the sunlight, photocatalysis. That's a photocatalysis, but the enhancement in the dark needs a thorough study. Degradation process identification is laborious task. Next slide, please. Yeah, thank you very much for the organizer for giving me the opportunity to present before you my work. But the question remains, why organic products in the presence of catalyst, uh, there is a degradation taking place. Whether is it called as it can be called as a photocatalysis or what? So if anybody of listeners here, if they can throw some light, I'll be very happy. Otherwise, I'm very thank you for giving me the opportunity. I close my talk here.
Thank you, Professor, for such an enlightening presentation on providing numerous ways to provide solutions to emerging pollutants. Now, the session is open for questions, if any. As I said earlier, you can either post the questions in the chat box or you can directly unmute the mic and ask the question to the speaker. So, there's a question in the chat box which says, Sir,
Yeah.
have you done any bioassay studies on treated water using photocatalysts such as fish toxicity studies?
Yeah, that work is being done. I don't want to present it here. Already done because these catalysts have got the see. Finally, the metal semiconductors, when you irradiate with the any radiation, electromagnetic radiation, the reactive oxygen species are formed. These reactive oxygen species, as you have seen, that they have very high oxidation potential, and these ROS, reactive oxygen species, have got tendency to enter into the microorganism and destroy them. So it is a very well known that the metal semiconductors have got potentiality to remove the microorganism. I have not done the exact work on that one. A few couple of semiconductors I have used, and we have found, especially that is BOD. BOD level is reduced. I can reduce the BOD level, and we have done it. So I have not presented here. It is okay. Finally, it is a ROS, and the formation ROS is the main thing in the semiconductor technology when we are irradiating the semiconductor. So yes, we are doing that particular. That is also an important aspect in our study. Have I replied you properly to whomsoever whoever asked that question?
Yes, sir. Thank you for answering the question. And now we will have a virtual visit to Meiji University, Japan, as stated, where the participants will be introduced to university campus and high-end instrumentation labs. Sorry to interrupt, sir. Sarani, am I audible?
Yeah, yeah.
So there is another question from Murthy sir, which
Hmm.
says metal oxide semiconductors, as mentioned by you, have shown degradation in the sunlight photocatalysis. Has any
Correct.
study been done on the band gap of the semiconductors?
Bench scale.
Band gap of
Hello.
these semiconductors.
No, these are all,
Uh,
see, whatever I have used, the semiconductors are all well studied semiconductors. I have not used anything. Titanium oxide is well studied, molybdenum oxide is well studied, iron oxides are well studied, zinc oxides are well studied, copper oxide. They have got perfect whatever the literature band gap. So I need not study their band gap because last 30 years I have been working on these catalysts, all these metal oxides. So we need not worry about. So especially titanium oxide has got 3.2 electron volt band gap, but I can modify by. Uh, uh, Hello, am I audible?
yes, sir, you are
Hello.
audible.
Yes,
Yeah.
sir. Yes, sir. Yes.
Yeah, so the band gap is not a immediate concern for me because they're all well-known semiconductors. There is no point about that one. Only thing is that they are all uh, uh, showing the ROS present in the water. That is the only thing. So I don't think the any band gap I had to study fresh because they're all well understood systems. Yeah. Anything?
A kind request to all the participants, if there is any questions, you all can post it in the chat box. If not, we can go ahead with the virtual visit to major university campus and instrumentation labs.
Hello.
Yes, sir?
Yeah, any more questions?
No, sir. No more questions. We are proceeding with the virtual visit video.
Yeah, yeah, that.
Hey, good morning. Isn't it nice to be traveling through downtown this early in the morning? Look at all these skyscrapers. We're in Nagoya right now, one of Japan's largest cities. My name is Max Fraber, and I'm a teacher at Meijo University. Nagoya is the central city of Aichi Prefecture and is located right in the middle of Japan. The city blends the latest advanced technology with ancient Japanese tradition. Have you ever heard of the feudal lords Nobunaga Oda, Hideyoshi Toyotomi, or Ieyasu Tokugawa? They united Japan in the 1500s, a period plagued by constant battles between opposing military leaders. Nagoya is famous for producing these three military commanders who had a huge impact on Japan's history. From very long ago, the region has been a transportation hub where industry and culture have flourished. In the Edo period, many craftsmen were gathered here to build Nagoya Castle. From that point forward, many different manufacturing industries were developed. Elaborate wooden mechanical robots called karakuri ningyo were produced in Aichi Prefecture. The superior skills and the spirit of craftsmanship laid the foundation for the development of the textile industry, which in turn evolved into Japan's world-leading industries such as the automotive, precision equipment, aerospace, and robotics industry. Meijo University is the largest private university in Nagoya, the city known as the manufacturing capital of Japan. Meijo University has 10 faculties, 25 departments, and 9 graduate courses. It is the area's largest private university, integrating the arts and sciences. The university's main campus is the Tempaku campus. The symbol of this campus is Tower 75, which is known as a landmark of academia in Nagoya. Yagoto campus pursues ideal education in pharmaceutical sciences by utilizing more than 50 years of tradition and achievement. Established in 2016, Nagoya Dome-mai campus provides open learning opportunities to the community and the world. These 3 unique campuses provide state-of-the-art education and research facilities which support the learning of more than 15,000 students. The founding spirit of Meijo University is to foster individuals who can become richly endowed with moderation and fairness, as well as have the ability to get things done while earning the trust of the nation and society. The university's mission is to foster people who see the essential nature of these things with humility, understand moderation, have a broad perspective and sense of equilibrium, are trusted by all, and have the ability to get things done. I was born in Boston, Massachusetts, in the United States. And it was through practicing Aikido at a very young age that I first became interested in Japanese culture, as well as Japanese language. In fact, I was lucky enough as a university student to be able to come to Japan and study for an entire year. When I first arrived, my first impression of Japanese people were that they were hardworking and they had a passion to take on new challenges. Now, after having spent half my life and having taught here for many, many years, I can honestly tell you that my first impressions haven't changed. Here at Meiji University, not only the students, but the teachers, they share this desire and passion for learning. It has been said that all great knowledge starts with small steps of learning. I am sure that this will remain true in the future. When he was a university student, Professor Isamu Akasaki's journey began from the inspiration he felt upon hearing that a Japanese person had won the Nobel Prize for the first time. He became resolved to accomplish something that had never been done before, no matter how small. Ultimately, Professor Akasaki's determination led to the invention of blue light emitting diodes, or LEDs. In recognition of this invention, Professor Akasaki was awarded the Nobel Prize in Physics in 2014. Professor Akira Yoshino became interested in science in elementary school when he read The Chemical History of a Candle by the British scientist Faraday. He went on to discover the lithium-ion battery, which became a driving force behind the spread of mobile electronic devices. Professor Yoshino was awarded the Nobel Prize in Chemistry in 2019. Professor Sumio Iijima discovered carbon nanotubes, which are sometimes referred to as a dream material. In recognition of his discovery, he received the 2015 European Inventor Award. Looking back, Professor Iijima describes his discovery as a blessing of serendipity. The potential of carbon nanotubes is further exemplified by the many academic papers written by Iijima and how they are some of the most frequently quoted papers in the world. At Meiji University, researchers are active on the forefront of international research and continuously challenge the possibilities of new learning. Meiji University is implementing new projects and new initiatives to greatly expand the possibilities of learning for both its faculty and its students. One such project is the MS-26 vision for cultivating lifelong learners. This project has been in anticipation for the year 2026, when Meiji University will celebrate its 100th anniversary. Even after students have graduated or completed their studies, it is our hope that they will continue to enjoy and engage in lifelong learning. With this in mind, Meiji University is providing support for these kinds of initiatives. Two examples are the Learning Community and the Enjoy Learning projects. Through partnerships with the local communities, corporations, and other universities, these initiatives have given birth to a series of new projects that go beyond the framework of Meiji University. Here at Meiji University, I've discovered even more learning possibilities. Also, by continuing to teach and to learn, I've been able to see firsthand the way the world continues to change. I believe that the mission of a university is to pursue the highest levels of learning. Meiji University is a place that enables continuous, lifelong learning.
I am Takahiro Maruyama, the Director of Nanomaterial Research Center in Meijō University. Supported by the Japanese government, we are proceeding with the project related to nanomaterials, that is, the private university research branding project. We are investigating various nanomaterials, including graphene and carbon nanotubes. We synthesize carbon nanotubes and graphene by using CVD, chemical vapor deposition. We have various types of CVD in our laboratory. This is a gas source type CVD system. This is a hot roll CVD, which is suitable for mass production of carbon nanotubes. This is a cold wall CVD, which enables minute control of feedstock gas. By using this system, we succeeded in small diameter single-walled carbon nanotubes using iridium catalysts. To characterize carbon nanotubes, graphene, and other nanomaterials, we have many kinds of facilities. In this room, there are many kinds of analysis equipment. This is XPS, X-ray photoelectron spectroscopy. This is SEM, scanning electron microscopy. This is AFM, atomic force microscopy. This is Raman spectroscopy. There are powerful tools to proceed with the research about nanomaterials in our research center. If you are interested in nanomaterials, please contact us.
We thank Meijō University for such an amazing university campus tour and enriching our knowledge with various equipments used in our labs for research. Now, the session we will break up for lunch and the participants are requested to join us for the post lunch session sharp at 2 p.m.